So far, we've basically exclusively been working within GHCi and exclusively been working within the expression sublanguage of Haskell. Now, when we start writing more interesting real Haskell programs, we have to go beyond that expression language and move to working with data types and functions. And that means that we also have to switch from just working within GHCi to working within an actual editor, and that we have to look more closely again at the structure of Haskell modules and the declarations within those modules. And in particular, we're going to start with so-called bindings. So bindings are the simplest and probably most important form of declaration. And a binding is giving a name to an expression so that it can be reused. Right? So in its simplest form, a binding just looks like this, that you have an expression, which is anything that we've already encountered before, and then you have an equals symbol, and on the left you give a name to that expression. So you have a name equals expression. Right, and then you give the name 5 to the expression 2 plus 3, and you can then use 5 to mean the same as 2 plus 3. So in particular, you can then go on and say 10 equals 5 plus 5, reusing the binding we've just made. Okay? And you can also use 5 in any other context. So here a list is another binding for an expression of list type, which again makes use of the binding 5 that we have already made before. Okay. Such bindings are typically put into Haskell modules, into a Haskell file in an editor. And such Haskell source files, they have the extension HS. And I'm going to show this now. So let me open up my editor with a file that I'm calling intro.hs. Okay. And as I've hinted at before, I have Haskell language server active, which is a Haskell support for the editor. So I'm getting sort of the power of GHC in the background. And in fact, this module intro where that appears here is not code that I've written, but is code that is being suggested to me by the editor because it would be a valid module header, right? But you don't have to give a module header in a module. So let's just for the time being just omit this, and let's just write 5 equals 2 plus 3 as we have done before. And again, you see that I get a suggestion for a type signature given here that I could be putting in. We haven't really been talking about type signatures yet, but they look a little bit like the information you got back from :T when asking GHCi. This is just suggested at the time being, or you can see it as informative, but I'm going to not take GHC or Haskell up on its suggestion and just continue typing in the examples that we had on the slides. Okay, and then we get something that looks like this. And we can see that we can reuse 5. In fact, we don't even have to define something before we use it in Haskell. So there can be only a single binding for a single name in the entire source file. And Haskell is actually allowing us to put them in any order. So I can define 10 to be 5 plus 5 before I actually define what 5 is. That is perfectly fine. Okay. I can then go and load my Haskell file into GHCi by saying GHCi intro.hs. and that will load this file. So you'll see that here, that it loads this. And if there are no errors, it'll give me a prompt. And then in GHCi, I can actually try out the things that I have been defining in the source file. So I can type 5 here now, and I get 5. I can type 10, or I can type a list, and I get these things evaluated in the way that I would expect them to be. And this is a very common mode of operating, right? So that you have a source file and you make changes to that source file, and you have GHCi open with that source file loaded at the same time. And I really encourage you to adopt that as well. It's not a lot of fun, and usually also not very successful, to just write code without ever trying it out and playing with it. So you should always make it a habit that the moment you have been writing a little bit of code, you should immediately load it into GHCi and try it out and see whether it behaves correctly, whether you learn certain things about it, whether there are things that you could improve, and so on and so forth. So that is a good habit. If we make changes, so if I make another definition here, let's say I define 6 equals 3 plus 3, much in the same style as before, and then I go back to this window and now I type in 6, then I'll get that 6 is not defined, because when I loaded the file, right, this definition was not yet there. So for this I have to reload the file in GHCi, and that there is a nice command for this, which is :r, that is saying that whatever file we're currently having loaded into GHCi is attempted to be reloaded, and then we see it's being compiled again, and after that reload we can type in 6. Okay. There is some minor thing, because I'm just seeing this with the infer types, that may actually be surprising to you, because we have been seeing before that the type of 3 is actually not integer or int, but it is num p double arrow p, or I mean the type variables and such infer types don't really matter, only whether they're different or the same. Could also think about it as num a double arrow a, but it is overloaded over the num type, and we know that plus is overloaded over the num type as well, and therefore 2 plus 3 or 3 plus 3 should be overloaded as well, right? Nevertheless, somehow GHC suggests the type integer here. What's going on here is a combination of two rather obscure Haskell features that are called defaulting and the monomorphism restriction, and I'll try to make a video about them later in the course. For now, all that I want to say is that under certain circumstances, for top-level definitions, GHC will not give you the most general inferred type that it normally would be able to give. It'll just make a more specific choice. And that is a little bit strange and perhaps even unfortunate, but that is how it is. The slide here says that one can make bindings directly in GHCi, and indeed that is possible, and sometimes I will certainly do this. So I can do something like x equals 4 plus 4 directly here, and then I can refer to x as well. But it behaves ever so slightly differently from Haskell source files. For example, I can make a new binding for x now in here, and that changes the meaning. It basically shadows the old meaning of x. That is something that is not possible in a module, and if we later have definitions that span multiple lines, then they are still possible to enter into GHCi, but they become very tedious to enter. In general, the habit should be that if you do something that is going beyond just typing in single line expressions in order to try something out, you should really go to a source file and make your definitions in the comfort of a full editor, and then load that source file into GHCi and try out the things there. Okay? So we've already seen that we can work with the bindings that we've loaded into GHCi, so I can skip this slide. Next is function bindings. So they're really at first no different from the bindings that we have already seen, because we have already seen that we can give a name to an expression. So in particular, I can give a name to an expression that is a lambda expression, and I can do something like this that says double is actually a function that takes an x and adds x to itself. And then if I load this and call double 3, I'll get 6. And if I call double 100, I get 200, and it actually works. Okay. Now, a more convenient and more idiomatic way is to move the function argument to the left-hand side of the equals. And that is what most people will be doing. So this binding a name directly to a lambda term works as a way to define a function, but syntactically more common is to move the x here to the left-hand side of the equals. And if I load this and then run it, it works in the same way as we have seen before. Okay. This also works with multiple arguments. So just like we can do a lambda term that, so let's, for example, say the distance between 2 points on a line, right, is the absolute value of x minus y. So now if I do distance of 3 and 8, that's 5, and the distance of 8 and 3 is also 5. So that is one way of defining the distance on a line. It has 2 arguments. We can move the 2 arguments to the left-hand side, just as we could also write lambda xy arrow and move the 2 arguments to the right-hand side. Again, the more idiomatic thing is to have them on the left. Okay. One word of warning that is listed here on the slides is regarding negative numbers. So you may want to double the number minus 10, and you may think you can type this like this. It's not an unreasonable expectation, but it does not work. If we type this, we'll get a type error message and something like involving no instance for num, or actually even worse, non-type variable argument and the constraint. So that is a rather difficult to read type error message, unfortunately. But what's happening here is that whether you have the space here or not, right, Haskell is going to see this as an attempted subtraction. Right? So it's going to say we are trying to subtract the number 10 from the function double. And remember, minus is something that is overloaded over the num class, and 10 is something that is overloaded over the num class. So this whole thing could actually work if a function such as double was an instance of the num class, but it isn't. And that is essentially, this is just like a slightly yet stranger way of saying that there is no num instance for this type of functions. And again, the reason here is that we have been doing something wrong with numbers. In this case, it's not that we've been using a number at the wrong place, but that we've been using the wrong way to write the negation of a number, the unary negation of a number. And there is a special syntax here that essentially says that if you want to denote a negative number, you have to be very careful about the parentization. So essentially, it's typically a good idea to enclose the negative number directly in parentheses. There are situations such as a list in which this is not directly necessary, but for example, to like prevent the Haskell parser from seeing it as an application of the binary minus operator, if there's anything there to the left that could be interpreted as the other argument to minus, then you have to use parentheses. So that is something to keep in mind. Okay. There's also a function negate, but that is much more difficult to type. That can be used to negate a number to create the negative number 10. So we could be doing this as well. Okay. Right, I've been listing this function before. Let's talk about type signatures. So I've been mentioning already that GHC is suggesting types to me. And indeed, if I ask GHCi about what's the inferred type for distance, then I get this. And in most cases, I said before, not all of them, but in most cases, the same type is going to be suggested by the editor if Haskell support is enabled here for attaching to the function. And if I had written this myself, or if I click on it, I get this extra line, and this is called a type signature for distance. So distance : num a double arrow a to a to a. We read this distance has the type as long as a is in the num class a to a to a, something like that. Type signatures, if they are given, right, they are being checked for correctness. So if I would give a nonsensical type signature, something that says a to bool, I would get an error message here that says that the expected type is now bool, but we have producing something of a different type, a. Right? So type signatures that are given are checked and enforced thereby, and that makes them really, really useful. So even though type signatures technically are optional, right, they're strongly encouraged to be put into place. Right? So, and I would really encourage you to do that. In fact, typically you should start with the type signature, and we'll see that in the upcoming parts of the course very often that we start with the type signature, because the type signature actually provides us with guidance. But also, very importantly, because type signatures are checked, type errors are better with explicit type signatures, much, much better, because often, because Haskell's type system is so flexible, if you don't give a type signature, you may end up writing something that is not what you wanted to write, and it actually has a different type, but it nevertheless can be given a type, right? And so you'll not get an error message immediately. It'll just not be what you thought you wrote. And then later when you start using it, you'll notice that you get errors because it has a different type from what you expected, or it behaves very differently from what you expected. And if you make your own expectation explicit by writing down a type signature, you'll immediately get the type signature checked against the code that you're writing, and you'll usually get a much better error message. So by all means, always write type signatures. And we should have done this for the other functions that we have been given as well, and also for the constants, really. Yes? So in the future, we'll always put type signatures in from now on. It's time for a little aside. We have been using quite a few functions already from the very, very beginning. I've been using things like not to negate a Boolean, or a plus operator, or the minimum function. Or the cons operator. And all these are library functions, actually. They're not built into Haskell. They're not keywords or hard-coded into Haskell, the language. They're coming from a library. And that goes back to the fact that Haskell code is organized into different modules, usually one file, one module correspondence. And typically, if you want to use code from a different module, you'll have to explicitly import it by means of an import declaration in the beginning of your module. But there is one special module, and that module is called the Prelude. And that module, the code from that module, the functions, data types, everything else that is exported from that module is implicitly available in any other Haskell module. And that is the reason why we do have these names and scope, plus, min, not, bool, true, false, all these kinds of types and values that we've already been using. They're all coming through the Prelude, which is implicitly available in any other Haskell module. But in principle, these are just Haskell identifiers. They could be renamed. They could be different implementations of the same types in other libraries. There's nothing really special about these names. Okay? That is also, by the way, the reason why if we just start GHCi without any arguments, we get Prelude here as the GHCi prompt, because it tells us that the Prelude is the scope, is basically is the module of which the functions that come from the Prelude are currently in scope for us to work with, right? And we have seen that this changes if I call GHCi with the intro.hs file to star main, and it also says compiling main, and that is because if I don't give an explicit module header, then the default name for a module that I'm defining is main. So here I'm loading the main module, and I have the things from the main module in scope, and that's why the main is listed here. But I additionally actually still get the Prelude things in scope, and that is like essentially not entirely precise, but that's essentially what the star here indicates. It tells me that I have slightly more in scope than just what is being defined in main. Right? So I still can use not here, but I can also use 6, which is defined in main. And if I decide to give an explicit module header here, and actually say I want to call this module intro, if you give a module an explicit name, then it should always be matching the name of the file. So in this case, intro.hs, so we call our module intro. Then if I reload it, the prompt of GHCi will also change to now saying star intro. Okay. All right, so next let's look at defining our own data type, our own first new data type. And this is I'm going to do this here as well, a data type that's called choice. And actually I'm going to give the definition first. And so this already works as a definition. So this defines a new data type, if I reload this, which is called choice. And it defines 3 so-called constructors of that data type that are called rock, paper, and scissors. And so I can ask what the type of rock is now, and I see that rock is a constant now of type choice. Paper is a constant of the new type choice, and scissors, again, is a constant of the new type choice. So I've defined a new data type, and that data type has 3 values. It's an enumeration type, if you like. The only 3 values of this type are rock, paper, and scissors. This bar here separates these so-called constructors, or these different options of different shapes. You can see this as a sort of or, so choice can be rock or paper or scissors. And these are the only 3 options that we have to form values of this type. If I now type rock into GHCi and want to have it evaluated, the idea of these constructors is that they evaluate to themselves, so that rock does not evaluate to anything, but it's just a value, right? So rock would print rock. But we run into a problem that I've been mentioning before, namely that not all types in Haskell have a show instance, and if you type something into GHCi, it tries to print it back using the print function, as we've seen before, and that requires a show instance for your data type. And if we define a new data type, it starts out with no class instances whatsoever. Right? Fortunately, GHC or Haskell makes it very easy for us to define certain, or to make our new data type an instance of certain classes in the obvious way by means of a construct that is called deriving. Deriving is only available for very few type classes, but show is one of them. And by just saying deriving show here, we make the choice data type an instance of the show class in the obvious way. And what does that mean? Well, it means that the textual representation of each of these constructors corresponds exactly to the names of these constructors. And that is what we probably would expect. And if I now reload, and if I now type rock again, I do get rock printed back as the result. Similarly for paper and scissors. Okay. I can still not do anything else with these values of type choice. I have to define further functions on them or make it an instance of more type classes. And, we'll see next how to define functions on such a type. So the main way in order to define functions in Haskell and that do something interesting, right, on data types is called pattern matching. And that is what we see in action here with the improve function. So we see that improve has a type signature that we can read. It's a function from choice to choice. But then rather than just having a single equation, it actually has 3 equations. And these 3 equations, they do not mention variables on the left-hand side for the arguments, such as our distance function or our double function did, but instead they mention the constructor names. And what's happening here is that we distinguish different cases by means of so-called pattern matching. So these rock, paper, scissors occurrences here on the left-hand side of the equals are called patterns, and constructors can be used as patterns. And if we call improve on a particular value, right, then Haskell will actually try to determine which of the patterns that I have been listing my concrete argument that I've been supplying matches. And in this case, for the choice data type having very simple shapes, only 3 possible values, pattern matching is trivial, right? If I call improve with rock, then the first equation matches. If I call improve with paper, then the second equation matches. If I call improve with scissors, then the third equation matches. And then depending on the matching equation, that equation is being used and the corresponding right-hand side is being returned. So let's try this out. So if I start writing improve, go from choice to choice. All right, and then I improve rock, and this is actually inspired by this game, rock, paper, scissors, where like 2 players are making a choice out of these 3 options, and for every choice there is another choice that wins against that choice. So ultimately the choices are being compared, and there is a stronger choice, but the ordering of the choices is interesting because it's cyclic, and if you have the choice rock, then the better choice is paper, because paper can be used to wrap up the rock. And if you have made the choice paper, then the better choice is scissors, because the scissors can be used to cut the paper. And if you have made the choice scissors, then the better choice is rock, because the rock can be used to blunt the scissors. Okay. And so if I write the definition like this and load it, I can actually call my function on these 3 values and get the corresponding results back. And that is a simple definition by pattern matching. Right? So that is a very simple data type and a very simple function definition by pattern matching. But this carries on to more complicated data types and more complicated functions, and will actually be what we're discussing in the foreseeable time span, the next few videos. This will keep us busy for quite some time, this notion of defining data types, defining functions by pattern matching on these data types, and all the interesting things we can do with them. Pattern matching is an incredibly powerful and important concept in Haskell, and this is our first encounter with it. Okay, so that's it for now. I will continue with a more interesting example, possibly in the next video.